All right. Hello, everybody. Welcome back. It's a Material World podcast with your co-host David Ye and my friend here, Puneeth. So, Puneeth, how you been doing?
I've been good. It's been a little bit of a busy summer with traveling, but also I recently passed one full year working here at Boston Scientific. Thank you. But it's been a lot of fun to make an impact in medical device industry, and I love the culture here. So really love the team that I'm working on, and excited for what's ahead. And that kind of ties into one potential application of our episode today. Do you want to dive into that?
Oh yeah, I think that today's episode is very interesting. We're talking about multi-metal printing, so 3D printing of metals, but there's multiple in there, and there are applications, especially on medical devices. And so he was talking a lot about bone integration, so I'm sure that's right down your alley. But it was very interesting to hear about how we can tune these implants and make them actually like help your recovery and even like not make your bones stronger, but get back to where you used to be, which I thought was very interesting. Maybe you can get more insight on that aspect.
Yeah, so that's the key part with implants, is that you can't make them just like totally like fully comprehensive to the point where, like, if it's a knee implant, like your actual like tissue doesn't grow back, or it doesn't fully recover, which is possible if you're kind of adding something into that scope. So that the potential for like 3D printed implants and creating lattice structures, which he talks about, allows for that tissue and everything there to grow back, and for your knee, for example, to fully recover. So I found that fascinating. He showed us what that looks like at a smaller scale on like a keychain. So if you're on YouTube, then you can see that, but also he explains that to our audio only listeners. So I thought that was super fascinating.
So do you think that we could ever have like an internal cast, like now just have like biodegradable materials or things that could be integrated into like the outer layers of your skin, and now no longer need a cast? Or do you think that's just science fiction?
I don't think it's science fiction. I think we're still years away from it, because there's just so much that goes into play. Kind of what he was talking about is that it's very difficult to create a material that has those like strength properties, but then can dissolve basically, or can degrade, which is the other aspect that you would need for these like internal casts. So we're still years away, and I feel like there's also all of the regulations, right? You need to do a lot of testing to make the FDA and all the other regulatory bodies like comfortable with these materials. So there's just a lot that goes into it, but I would never rule it out. I think it's definitely possible.
Yeah, one of my favorite analogies was when I was in the polymer industry working on biodegradable polymers. It's like you want a water bottle that will biodegrade, but you don't want it to biodegrade in your cabinet. And the difference between your cabinet and a landfill are actually not as many as you would think. And so it is hard to tread that fine line between like biodegradable and also the strength that you need and these like the length that you need, because it takes like what, like 6 weeks for like a bone to heal. I'm not sure. Don't quote me on that. I'm not a doctor.
Good disclaimer.
But yeah, I think also he brings up a really good point in our conversation about how the technology is moving so fast. And so what was considered impossible 20 years ago are now possible. And so he kind of put it bluntly, but he's like, just join it and you're going to see it fly by your eyes. Mm-hmm. And I think that that's really interesting and is inspiring to be part of like the next technological revolution.
Yeah, absolutely. That was one of my favorite aspects of like his advice that he gave at the end of the episode, is just jump in and then just like enjoy the ride, right? So he keeps it simple, but it's still like very inspiring, kind of the work that he's doing, and how much he loves like the work he's doing. So yeah, it's a great episode. make sure to stick to the end. And before that, also leave us a rating and review on Spotify and Apple. It would really help us out. So without further ado, let's get into it.
Our sponsor today is Johnson Matthey. Are you a material scientist or engineer who wants to be part of the drive for a world that is healthy and cleaner, both for today and for future generations? By understanding the relationship between a material structure and its physical properties and chemical behavior, material scientists and engineers at Johnson Matthey develop sustainable technologies that are catalyzing the zero transition in transport, chemicals, and energy. They design porous materials for catalyst supports for emission control systems that remove harmful emissions produced by diesel and gasoline engines. They innovate new compositions for catalysts at the heart of the hydrogen fuel cells in trucks and buses. And they also develop new corrosion-resistant reactors for processes that enable the production of sustainable chemicals and fuels. To find out more, visit matthey.com, that's MATTHEY.com. Johnson Matthey, inspiring science, enhancing life.
Hey everyone, we are very excited to welcome today's guest, Dr. Bram Neirinck, manager of Sintered Solutions at Aerosint. Bram has a PhD in material science and a wide variety of specialties, including R&D, powder technology, and metallurgy. And in addition to his role at Aerosint, he is also a senior R&D engineer at Antleron. So we're very excited to have you. Thank you so much for joining us today, Bram.
Thanks for having me. Thanks for letting me talk about something I like.
No problem. So yeah, we're super excited to talk about it because we think it's very unique and builds upon the foundations of others. So let's just start out with the basics. What exactly is selective powder deposition and how does it enable us to multi-metal print?
Well, before we immediately jump into the deep with multi-metal printing, let's just talk about what powder does in 3D printing, or additive manufacturing as they like to call it in industry. I think additive manufacturing sounds a bit more professional, industrial, while 3D printing is more for home use. So in AM or additive manufacturing, you construct pieces by adding material typically in a layer by layer fashion. You can do this with several feedstocks. You can use a liquid resin that you cure. You can use a filament that you melt. But most of the industrial processes actually use powder. And that occurs by spreading a thin layer of powder of a known thickness on a build plate. Then locally you fuse this powder together. Maybe it's easy if I get apart. So you spread a pattern. Then locally you fuse that one layer together. And that's then you lower the build plate and you spread another exactly the same thickness layer of powder and fuse again. The fusing can be done using a binder then sintering, using laser, using electron beam, plenty of options. So in traditional processing, you have a single powder that you use and you use like a roller or a blade to scrape it on the powder bed. And that means that all your parts are made of a single material. What Aerosint does is we developed a system to deposit multiple powders in the same powder bed. It's based on a roll-on-roll-off system. If you imagine a drum, well, we'll use a bottle. If you imagine a drum, there's a scraper on top. You have some powder on the drum. As the drum rotates, it scrapes a thin layer of powder onto the drum. And then as it rotates and moves over the powder bed, in sections below the drum, we have internal actuators that can release a small section of powder. So it falls onto the powder bed and makes a 2D image that way. And because you control the area, you can change the shape of the powder bed, you can change the shape of the position. And by adding more drums, you can deposit multiple materials. And then after that, the rest of the process is actually the same as in the additive technique you're using. You can use a laser or binder or anything to fuse the powder together and then apply the next layer. And as you said, yeah, like the example, you can use that to print multi-material parts. You can also do other things with it. For instance, material waste is a big issue, especially in polymers. The polymers degrade during the 3D printing because the entire print chamber is hot. That means that after print job, the powder that you don't use, often we need to throw away 20, 30, up to 50% away of it. If you could replace that powder with something which doesn't degrade, you can save on material and you just deposit the printing material where you want it. Or in industrial printing, the printers are getting huge. Like I see that they're now going to launch a printer from E+3D, which has a height of more than a meter, half a meter by half a meter. Yeah, if you fill that completely with powder, you're speaking about literal tons of material that is in there, both in weight and in value, because printing powder is not super cheap. So if something happens with that powder, it means you can throw away the entire batch. And it makes it more difficult for the machines to be constructed because so heavy. What we could do technically is just deposit the powder where we print, and for instance, print a wall around your sample that you're printing, like a hit box or a bounding box, and then keep printing up. So you only have a fraction of the powder which you would need to fill the entire machine, but just enough to make your part.
Wow. So what are the challenges that come with incorporating multiple metals and I guess, integrating the two? And how do you identify which materials kind of integrate best?
That is the complete material science which is behind it right now. And that's one of the parts where we work on most. And we sell a lot of our equipment out to universities who do the research to work on those materials. And it all starts with printing simple cubes. And then you cut them in half and look at what the interface looks like. And you use that to optimize the parameters to see how you can weld them together. If you need like overlapping parameters as well, you scan your laser, or if you need a different sintering approach. That's the basic material science behind everything. But it was also the case for monomaterial printing. When they started with 3D printing, all the parameters had to be developed. So it's basically the same process.
And so I think most of our listeners are very familiar with 3D printing, as you would say, like at home, where you have a filament printer printing some sort of 3D structure. Could you kind of explain some of the differences and maybe the speed and accuracy compared like a 3D printer at home and what you're talking about with like laser bed, like sintering?
Yep. Well, the home printers, both the resin and the FFF printers, the fused filament type, they are printing polymers. The FFF printers, the ones with the filament, print the thermoplastic polymers, so it gets hot and it melts and it fuses together. The resin ones print resin that is cured and that becomes a thermo harder. Those techniques are both used in industrial applications as well, sometimes with a bit more high engineering materials, which makes it a bit more expensive. But in the powder printers, basically you have two classes. You have the big SLS polymer printers. I actually have an example of something which was printed in polymer. This is the system that HP developed. They print like that. That's fusing of those polymers. The size of the printers are typically bigger. The resolution is not necessarily higher for the parts, but it's the reproducibility of the entire process which is important. So they make sure that if you design a part and you print it, it gets out the same each time, because this is a production process. And a lot of the validation and work on industrial printers isn't there. And then also the design software and the tools you use to optimize the local properties of your parts you print.
Got it. So David just mentioned the laser bed sintering, and I want to dive into that a little bit more and the integration of your technology in there. So can you start by just explaining what laser bed fusion or LBF is, and then how your technology, kind of the multi-metal side of it, can be integrated into that process?
Yep. So laser powder bed fusion, the name says it all. You use a laser to fuse powder together, and LPBF is specifically for metal powder. You also have selective laser sintering, which is for polymer. But yeah, in LPBF, you use a laser to locally melt the powder, and molten liquid powder either attaches to the build plate or parts layers which you have printed before beneath it. It basically welds the liquid material to what is below, and the entire science behind it and the methodology is completely based on laser welding. So when they started LPBF, they already had some knowledge on laser welding, and they used that to determine parameters. Now our tech is basically replaces one part of that machine, the recoater, which is normally just a blade that recoats the powder. We replace that. The limitation for us is the size that is available in the machine, but if there is space, we can put it in and it should work with any commercial system if there is space. Yeah, currently we work together with one company from Germany that offers it as a commercial printer, but we're open to work with anyone. And we actually sell our recoater as well to universities who build their own setup for experiments and want to build it into their own device.
And so for this powder system, you mentioned it briefly before, but you have this ginormous system with tons of material in it. And so with your LBF, for LBF and your very selective deposition, does that allow us to cut down on waste? And how does allowing us like selectively put multi-materials affect the overall usage of the system?
Yeah, you can cut down on waste on two ways. Like I try to explain, you can build a wall around the part you print and just deposit in one section of the build plate. What we're also aiming at, and that will be more easy to sell, is that we use an extra material that we then fill up the entire powder bed with. That can be powder that has already been used several times and has gone out of spec, but is still the same material as you otherwise use. That can be something inert, which is easy to separate, but that will be a bit more difficult because if you add different materials in a printing process, you run into the validation and of the process again. If you have contamination in metal parts of something else, it's not that good. One discussion I've had with a lot of industrial sectors, both from aerospace and medical, is on the printing of titanium. Titanium has a tendency to degrade over time when you use it in a printer. It really sucks up all the available oxygen and nitrogen in the atmosphere. And even if you use bottles of inert gas, you always have small leaks, you always have small contaminations in those bottles. So it is well known that if your printer is not working optimally, your titanium can degrade over time. But that is a problem because that means also the material specs of the parts you print change over time as the powder has been reused. And both aerospace and medical really don't like that because they're very regulated sectors. So there's actually currently big discussions ongoing in the ASTM and ISO boards trying to standardize 3D printing on how much time titanium should be reused and what kind of validation on the powder is needed in between each print. What we could do is just deposit virgin fresh powder where you want to print it, fill the rest of the bed with something which has been used. And even then, if a couple of particles of that used powder get into the part, they basically have the same chemical makeup, just a little bit more oxygen or nitrogen, and it will not affect the overall performance.
Wow. So I guess that's especially important, I know, with the medical device industry, because titanium, I know, is used in like those 3D printed implants. And so you mentioned kind of the challenges that come with titanium originally. I'm just curious, what are some of those like optimal materials or like easier to like print materials from the metal side?
Well, actually, titanium is one of the easier to print materials.
Oh.
Strangely. The way the microstructure works and the metallography works, it is a quite flexible and easy material to print. It also has a high boiling point in the liquid stage, which means there is less smoke involved. If you would see a metal printer in action, some materials really give off a vapor. We call it fumes, which is evaporated metal that then condensate as nanoparticles in the printer, and you need a gas flow to remove them. That can mess up a system, but titanium has very little issues with that. Other materials that are very common and that are easy to print, and they were of the first materials that were printed, are things like 316L stainless steel that prints very easily. Inconel prints nice and easily, but there are a lot of other powder materials which have been used in traditional powder metallurgy that don't work at all because the LPBF process is quite violent. You actually completely melt and cool down your material very fast. And some materials don't like it. They start cracking, they develop micro cracks, they develop a weird microstructures, or develop a lot of stress. And in that case, they don't like to be printed. But you have other printing techniques which are then complementary, which might be usable with those materials, like binder jetting, where you glue the particles together with a binder, and then afterwards sinter it. That process is much closer to traditional powder metallurgy than LPBF.
And so with all of this, especially with the medical industry, of course, Aerosint is focusing on multi-material printing. So how can you then take upon these ideas that you have and then add these multi-metal components to then enhance the value? And could you maybe explain some of the applications of the multi-metal in medical parts?
Yeah, the medical industry it's actually kind of weird that they jumped onto 3D printing additive manufacturing so fast, because they're a very regulated industry, but there are some very specific advantages for them for having printed parts. One of them is custom implants. You cannot produce custom implants each time. If you have a standardized machining production process, you would need to use new tooling each time. The second one is, and this is not a real implant, it's just an example. You can get these kind of porous structures printed that are not able to be machined.
Bram, can you talk through what you're showing on the screen right now for our audio only listeners?
Yeah, I'm actually showing a keychain that resembles a hip implant, and the top section of the keychain is made of what is called a lattice structure, which is a porous structure constructed of all interconnected beams.
Wow.
So, wow, that's cool.
Yeah, so these kind of structures can be printed quite easily, and they're very advantageous for orthopedic implants for two different reasons. The first is the holes provide a place for bone to grow into and to anchor the implant in place. In more old-fashioned orthopedic surgery, they were using what is called bone cement, which is a kind of epoxy that they inject and then cures around the implant in place. But if then something happens with the implant, or they need a revision surgery, so you get an infection and the implant needs to be removed, they need to scrape all that glue out again, and it's basically a big mess. With this kind of system, you have less infections, but also, yeah, you don't have any foreign material added. Second advantage of those porous structures is they actually affect the stiffness of the implant, and that makes it that it's better matched to bone. In nature, if you, for instance, have a crack in a tree, you will see that extra wood will grow around that crack to compensate for the extra stress and to make the tree strong again. Or if astronauts go into space, they need to keep exercising or their bones will start degrading. You have the same with implants. If you put a strong implant in a bone and that implant takes up all the force, all the bone around it will start getting brittle and desorbing. But if you match the stiffness of the implant towards the stiffness of the bone and you get this kind of springy implant, the bone will still see a stress, it will still see some force, and it will like it, and it will keep growing and really support the implant. Now, for traditional metal printing, you can only use one material, so you use a titanium alloy, and most of the cases it's a titanium alloy they call grade 23 or extra low interstitial to build the entire implant out of one material. That has somewhere, it's a compromise between a strong titanium alloy and a more springy one. What you could do with multi-material is take it the next step further, make the parts which are completely solid or just a core that is solid out of a strong alloy, and then make the surface and the parts which connect to the bone out of an extra springy implant, so you need less porosity, or you can tune the properties locally to increase the healing process and increase the integration a bit more. And lastly, this is more towards the future, people are looking now more and more in academia to implants that dissolve in the body. The idea is that as the implant dissolves, your bone starts growing around it, replaces the implant, and in the end, you have more bone at the original damaged structure than implant. Only those materials tend to be not mechanically super strong. There's some issue with controlling the dissolution strength. So maybe adding an extra material there that, like a strong core and then dissolution where you want the bone to grow, could help as well.
Wow.
And so when we talk about the medical industry, you're talking about like kind of optimizing it for each person's needs.
Yeah.
So could you walk us through kind of how a researcher or your team would work on finding what blends of titanium would work best, or through that process to create a customized part?
Oh, that's a difficult one because we actually don't do it in-house. I know from my previous experience that making a custom implant was mostly based on CT scans of the person, and then they modeled it towards there. But you can also model the bone to see where the loads are and how big the loads are going to be when a normal person walks on it, and then modify locally with some machine learning or artificial intelligence the e-models of the structure locally by changing the amount of porosity or adding a different material. This kind of design where you basically generate the structures based on simulations is getting quite big in the additive. I will see if I have, well, this is a silly example, but it shows the kind of organic structures you can get. This one as well.
Can you talk us through what you're showing right now?
Yeah, so I'm showing you what are well, these are voronoi,s but they're very similar to organic structures you get when you automatically generate a structure based on local stress distribution and optimizing that stress distribution. There are software tools called generative design tools that allow, based on inputs from stress zones, from where the forces are, to generate an optimized mechanical structure that then distributes the load completely. Well, you could do the same with multiple materials by adding a material. It would just be an extra parameter you add that allows you to change the properties locally. And titanium alloy combinations should actually be a quite easy one to print, even in LPBF, because they have a very close match thermal expansion, close match melting temperature, and basically they are all weldable on each other, so they should be co-printable. And you can even find papers of people who have already done that in more classical machines. They started printing with one alloy, then remove all the powder, put a new alloy in, and then continue printing. They have a change in composition at one point in the Z, but I could see that they could weld it perfectly together.
Interesting. So maybe I missed this, Bram, but what is that material that often complements titanium and when you're moving to this multi-material stage for 3D printing? Like I know you mentioned strength and springiness, right?
Yeah, you basically have 4 titanium alloys which are commonly used: grade 1, grade 2, grade 5, and grade 23. Grade 5 is the really strong one. Grade 23 is the average, good in all cases, master of none. Grade 1 is very flexible and very soft, and grade 2 is a bit stiffer than grade 1. Grade 1 and grade 2 are commercially pure titanium, so pure titanium but with different contents of oxygen. Grade 5 and grade 23 are technically the same, but with different concentrations of oxygen. And for lots of dental implants, they use grade 1. For lots of orthopedic implants, they use grade 23. But there has also been some research towards shape memory alloys, which can be titanium-based, like nitinol, that are very springy, that have very specific properties that might be interesting for implant structures as well.
Cool. And so in the case of nitinol, so I know with titanium, it has like the inert oxide layer, the titanium oxide that allows it to be biocompatible. Is it similar with the nickel aspect of it?
It is similar, but of course you still have nickel in the body. But what you technically could also do is, if you have an alloy which is not compatible with the body, and there have been some discussions even on the grade 23, which is now the standard alloy because it contains aluminum, which is suspected of causing some long-term issues, is to basically encase it completely in a commercially pure titanium in a grade 1.
And so you're talking about all these different grades of titanium, but with multi-metal printing, you can do other types of metals. Is there been like a theoretical limit to how many different types of materials you can print at once? Or I know there has to be a lot of drawbacks to adding more materials. So could you walk us through that?
There is first of all a mechanical limit because we have 1 drum per material. So adding more materials would require a lot more space. Edouard or CEO, as a joke, posted a sketch of a 10 material recoater, which was like a meter long. And strangely, people said, yeah, 10 maybe not much. 3, 4, 5 could be interesting. As far as the metallurgical limits, that's harder to discuss. Then you really need to look at the chemical compatibility and the thermal compatibility of your materials. And we are involved with printing cubes and with all the printing test samples in some research projects. But honestly, we cannot do the complete research on that ourselves. And that's why we are very happy to sell our equipment to research institutes who are much better equipped than us to do that basic research.
So I guess quick question there is what was the motivation to partner with these universities, and what has that enabled in terms of you being able to focus kind of on that core technology and then being able to leverage universities' time and resources? What has that led to?
Well, basically, our technology is a fancy new toy for them. So to be able to combine materials is just scientifically extremely interesting. Like I said, people have been, we have the first commercial system, but people have been building ways of printing multiple metals, even in powder bed in universities for a while now. Earliest paper I found was from 2008. And also they use standard printers to start printing one material, then replace the material and continue printing on. So there is already a scientific interest. But there is also lots of applications towards improving thermal performance, improving strength, locally improving hardness, and those kind of industrial applications also fuel research. A lot of research projects are still are application minded. A very limited amount of them is pure fundamental. So yeah, how can we convince universities of buying our equipment? Basically because they already want it. They want to do the research. They want to figure out what is going on. They want to be part of the next evolution in 3D printing.
That's fascinating. So then we can kind of move on to another heavily regulated industry, aerospace, and in particular, jet engine manufacturing. So I know we've done an episode on super alloys and jet engines previously, which David and I really enjoyed. How can your technology, how can the opportunity for multi-metal 3D printing make an impact in the aerospace field?
Yeah, aerospace is probably the second industry, or maybe the first with medical, that they really embraced additive manufacturing. Basically, in aerospace, everything revolves around maximizing performance while reducing weight and fuel consumption. And that is not only in the jet engines, it's also in structural parts of airplanes. Towards jet engines in specific, it has caused such a big investment in additive manufacturing that even one of the bigger jet engine producers bought two of the well-known brands of OEM machine builders just for the technology outright, and is investing a lot in developing new technology to print new materials. Am I allowed to see the names of the companies?
Yeah.
General Electric, they bought Concept Laser, which is now a GE Additive, and Arcam.
Nice.
Concept Laser was one of the very first companies to sell commercial LPBF machines. Arcam sells EBM machines, and they're doing a lot of work on binder jetting as well. So yeah, for jet engines, mostly thermal performance is really important. And additive manufacturing there can be a big help because you can print internal cooling channels in places where you like it, get it really close to the hot zones and optimize cooling. But still, yeah, you have an issue that you still need a high temperature resistant material. And those high temperature resistant materials are typically not very well conductive. And the very well conductive materials like copper and aluminum cannot withstand the high temperature. So you can combine the improved cooling with the cooling channels with also a more conductive material to more efficiently remove the heat and move it away. Now, the big block I showed you is actually a mock-up of a cooling channel. You can see some holes inside. There is a copper core and a steel outside. You can imagine something similar in a steel and a propulsion system where the blades, for instance, which are in contact with the hot gas, the outside is made of an Inconel, a high temperature alloy, and then inside where you have the cooling fans, the cooling tubes, that you have a core of copper, which more effectively draws the heat from the Inconel surface towards the cooling water and then away from the engine.
Why is it important for the blade turbine engine blades to be cooled for the plane?
You would actually need to ask for a propulsion engineer for that. But basically, they work, if I remember correctly, the higher temperature they can work at, the more efficient they can work. But yeah, if you have high temperatures, your materials also need to survive. But there's other places where fluid flow and gas flow is important, like providing the fuel towards the engine, providing sufficient oxygen to the engine. If you see one of the demo parts that GE has been showing off a lot, it's basically just the injection system for the fuel towards the engine that is increasing fuel efficiency just by optimizing that design.
Yeah, so I interned virtually at GE Aviation / GE Additive, and they really harped on the future or the potential of additive manufacturing within their engines and how it can, there's a lot of complex parts that go into these jet engines. So it can help in terms of reducing the number of singular parts needed to create those complex structures. So with all of that being said, I was just wondering, what is that marginal advantage, or where do you see the advantages of multi-metal printing over traditional single metal 3D printed parts?
It will just be the next step. You can just drive that advantage of 3D printing just a little bit further. And even marginal steps are important. Like for structural parts, Airbus invented their own aluminum alloy just to be able to print slightly lighter parts, which are still strong enough. A scam alloy, that's an Airbus patent. Every small step provides an advantage. And there's an ice cream truck driving to my street. So yeah, every small step provides an extra advantage, and all those small extra additional steps, they all going up, build up, getting a big advantage in the end.
Yeah, I think one of my favorite stories is like they removed all the SkyMall magazines and ended up saving like millions of dollars on fuel. So
Yep.
I think it's really evident that just small little incremental steps saves like millions of dollars for these giant planes and systems. For multi-metal printing, so now that I understand better, it's basically for the longevity of the material. I know that for aviation, maintenance is a very large time sink. Does multi-metals play a role in how we could reduce maintenance time?
I'm not 100% sure, but I think it's the same as regular additive manufacturing. They reduce the number of parts by using AM parts and optimize designs. And if you reduce the number of parts that needs to be bolted together and constructed together, you also reduce the failure points. If you construct something out of multiple parts by brazing different alloys together, because one alloy is needed in one zone and another alloy is needed in another zone because of temperature, because of stress, because of strength. Yeah, if you can print it in one part, that's again a failure point in those brazing connections that's removed.
Cool. So in my mind, it seems like that next potential leveling up is being able to put together materials that haven't previously been like combined in these settings. And you mentioned in a previous call the potential for machine learning and artificial intelligence to allow us to combine materials that were previously incompatible. Do you have any examples or any like dream materials that you could possibly create with your technology and with the power of ML and AI?
Yep. Well, machine learning and artificial intelligence are already used in 3D printing, partially in the computer-aided design, the generative design. That's a part of machine learning, but it's also been investigated by some even commercial players on optimizing print parameters locally for parts. You used to have just single parameters, say for a bulk material, for a fine material, for a scaffold, but those borders are getting a bit fuzzy and they don't always cover all the cases. So now people are working on making a kind of machine learning approach towards optimizing those parameters. And something similar could be done towards multi-metal. Once you know what is needed to combine two metals together, that you can generate like fuzzy parameters that change gradually to improve two materials to being fused together. Now, my dream combination would probably be steel and aluminum. One simple reason: steel is still the king in hardness and in strength and is still the most widely used construction metal, especially tool steel. And aluminum is still the lightweight metal of choice because it's not as expensive as magnesium. It's not as difficult to work with as magnesium, but it's still extremely light. Unfortunately, those two materials don't play well together in a metallurgical point of view. If you add a little bit of aluminum to steel, you completely ruin its mechanical properties, and kind of the same for some iron in aluminum. But also, the thermal properties are quite incompatible. If you would want to sinter them together, aluminum starts melting before the steel even starts sintering. The same if you use laser systems to build up a part. Your aluminum is so conductive it will suck the heat out of the steel parts while you melt them and might actually start melting them itself. So that's not an easy thing to solve, and most metallurgists would now say that those probably are not combinable, but you should never say never in science. I know of at least two processes in which they succeed in combining steel and aluminum. One is explosive welding, where they literally put two sheets of metal against each other and then create an explosion outside, and the force causes the two materials to weld together without actually melting anything. And the other one is a technique that uses extremely high currents to sinter powders together of these dissimilar materials, and it goes so fast that the material basically doesn't get the chance to melt. It even doesn't get the chance to oxidize. They do it just in air. So, and because LPBF is already a quite violent process, with those examples, I think there might be a route on trying to combine them, even if it's not by melting them completely to each other. Your laser is accurate enough that you might be able to form some kind of mechanical interlock that they then in post-processing can fuse together to get one single part. And the machine learning and additive hopefully helps in explaining and finding potential routes to how that might be possible.
Yeah, in a previous episode, we talked with someone from NASA, and they were telling us about how in space, metals will weld to each other as there's no oxide layer to protect it. And so that might be another avenue even. But I really enjoyed your answer, which was something very commonplace and ordinary. And I think a lot of times people would give like this crazy metal and this other crazy metal, but I think it shows the importance of just the basics. And if we can change steel and just change it a little bit to make it better, like everything's made out of steel, so then it would have the largest impact, which I really liked.
And even comparing two steel types together might already have a huge impact. You can have one which is corrosion resistant, for instance, for contact with the elements, but stainless steels are not the strongest, and then have a super strong internal core to make something really last for a long time.
Yeah, and what it could potentially enable is also super fun to think about too, right? If you're able to like integrate steel and aluminum, I feel like that would make a huge impact in like the automotive industry or anything like that. So that's all super fascinating. Do you have any, I guess, in your mind, what do you think that, what are the possibilities that could come if you were able to effectively integrate steel and aluminum?
Basically, everything which is lightweighting, because then you can use the steel parts to bolt to connect to weld to, and then use the aluminum parts to basically make the structure light. It will also be more vibration dampening. So, for instance, yeah, if you say automotive, think of big chassis elements that you make out of aluminum and steel. The steel where you can expect an impact. The aluminum for the bulk structure, brackets in airplanes that are now made of this really expensive scam alloy because the regular aluminum is not strong enough that you then can combine with two cheaper materials. There are too many applications to. If you have another hour or three, we can happily invent some.
So I think that transition is nice. Is like, so let's jump ahead and say we are able to make this new alloy. Things that you touched on before were the fact that we will have to validate and standardize everything that's made with this technology. And I think it's something that a lot of new people to the industry never think about. They think the big challenge is just making the product, but an even bigger challenge is ramping it up so that it's the same for millions of people. How are Aerosint, or maybe your philosophy on how do you work through and get that repeatability needed to be able to mass produce things?
In short, at the moment, we don't and we can't. All we do at the moment is try to get our technology out there to make it as good as we can. So it is ready for serious production, so you can reliably produce with it. You will first need to produce a ton of parts that you test before you get any database on seeing if it can be reliable. And yeah, so it's still very much in the research stage. There's still the university is still working on building the knowledge base that's just needed to do something like that. And there's simply also no standards available for multi-metal parts. Even for parts which have been welded or constructed vibration, there are no standards for testing those. Even for standard additive manufacturing, the single material additive manufacturing, standardization discussions are still ongoing, also towards validation, to long-term validation, to fatigue. But the entire industry is working together, and it's driven a lot by both the aerospace and the medical industry, because they know the value of a good standardization, good practices for repeatability to make sure that nothing happens with the parts they make. Yeah, and that's why we work together with universities. It might sound a bit disappointing, like multi-metal printing is still a pipe dream, especially with all the materials challenges that are still in there. But if you look back 20 years, metal printing was not really a big thing yet. It was just starting. And it took 5-10 years before its really cards started getting adopted and before the first real standards were getting out there. The first applications for metal printing were basic rapid prototyping, just some things to test that were then later machined, or, and this is going to sound strange, luxury goods and design items. Things where the mechanical importance is not that high, but the appearance and the funky appearance you can get with 3D printing is important. And I might have another example. This is something which is made via sintering of powder in a die, deposited door system. It's basically a checkerboard of copper and stainless steel, both in Z and in XY. I have been making some of these blanks as demonstration samples, because if you can just, the sintering process itself is quite simple. It's just hot pressing. If you can make these in that way, this kind of discs can be easily made with our set system by filling a die. They can then be blanks for machining for more designy items. And if the interface is not completely perfect from a metallurgical point of view, the guys who want this kind of stuff don't care too much about it.
You mentioned kind of like the main disadvantage here is time, right? Like you're catching up to some of these processes that have been able to be refined over decades. So how do you think there is a lot of power or like or potential in terms of having like communal shared databases to like gather a lot of data and then be able to leverage maybe these tools like machine learning and AI to iterate and improve at a more rapid pace? Or do you think that the like competitive advantage that comes with holding proprietary information will kind of rule supreme over the possibility of like a communal database spread over multiple companies and universities?
That is kind of a scary question, because I come from another big OEM on metal printing, and they keep their databases of sintering of parameters completely to themselves, and they sell them. That's something that can be sold. Also, you see some developments towards metal printing without supports. The way they do that, you can be guaranteed that they will try to keep it silent and off the grid as long as possible, because it's a commercial advantage. On the other hand, most of the real developments on metal printing, the initial ones, were all done in academia. And we've seen how far they came in academia over less than a decade. Now they already have the experience of how to approach developing those kind of parameter sets and those kinds of process routes. I guess it will, once they get their hands on multi-material equipment, it will just go faster, because they already have the backbone, the background on how to approach this kind of issues. But yeah, communal data sets, I'm afraid that metal printing, as long as it's in the hands of big industrial players, will never be something completely open source, though cheaper printers are coming out every year. You can get actually a metal printer for, what, 80,000? No?
It's still a lot of money to me.
It's still
Yeah.
a lot of money, but it gets in the towards the reality that smaller shops, smaller workshops can start thinking about buying it. Small universities, small research group can start thinking of buying it. But yeah, even the polymer printers used to cost a small house, but they're now getting affordable.
What was the price of a metal printer like, say, 5 years ago?
Around 10 times that, and there are still printers on the market of 10 times that price. The multi-laser ones, a single fiber laser can set you back 15 to 40K, depending on the power output, the color. So if you add 5 lasers, yeah, you already add a capital just in laser equipment. Those cheaper printers, by the way, use a different laser technology. They use diode lasers instead of fiber lasers. So the spot is a bit bigger, it's a bit coarser. They don't use a galvo to move the spot around. They use an XY writer, but technically they can still print metal parts that are functional.
Wow. Yeah, it's really interesting to see just how far we've come in such a short period of time. So that kind of tells me that there's a lot of room for accelerated growth in the near future. And so we've covered a wide variety of applications of multi-material 3D printing today. So first of all, thank you for joining us. We're very appreciative of your time. And to maybe wrap up the episode, can you share some advice for younger material science and engineering students looking to get involved in 3D printing in one way or another?
Oh, sure. My biggest advice is don't dream of the future. You can live it right now and you can experience it as it is formed. It like we just discussed, it is moving so fast. If you jump into 3D printing research or join a 3D printing group or company, you will see it moving along and evolving in front of your ears. What you can do with 3D printing grows every year, and that's not just metals, that's polymers as well, that's ceramics. Ceramics is a big one right now, and there's plenty of opportunities on this roller coaster. So if you like material science, or even if you just like engineering or mechanical engineering, there's lots of work also for guys who specialize in designing for additive manufacturing. There is plenty of work to do. And on the plus side, as an engineer or as a scientist in that field, you can make a decent living as well.
Absolutely. Yeah. For sure. Well, we're very appreciative. Thank you so much, Bram, for joining us today. It was a pleasure having you. As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.